Hi, my name is Grace Drew, and this is my physics lab 4 on oscillations. So the purpose of this lab was to compare predicted motion, which we calculated via a computational model, versus observed motion via provided video of an object oscillating on a spring. The difference was then plotted on a graph, including the x and y components. To do this, we first modeled the observed motion using tracker and a provided video, and the results of the total oscillation were recorded. And then we used a computational model via GlowScript and then inputted our results from tracker in order to graph them against each other. Our results showed that the predicted and observed motion were very similar and that the total change in energy was around 0. Some key concepts we needed to complete this lab were Newton's second law, which you can see below. We've used this in the past few labs. The energy principle, which is the delta E system equals the work done in the surroundings plus Q. And the format we used in this lab was delta E system equals delta K plus delta UG plus delta US. And then the formula below breaks that down even further, and you'll see where we input that later into our code. Other useful equations are the translational kinetic energy equation, gravitational potential energy equation, and spring potential energy equation. Here you can see the computational model conditions, and this is used typically the way we use tracker by setting up the axes, and then it was tracked and graphed throughout the entire video and the entire oscillation of the spring. After that, it was time to do the computational model. So to begin, we inputted some initial conditions, such as its mass, which is 0.407 kilograms, the initial velocity, or the initial position, which we got from the graph provided in the past computational model as well, and then the initial velocity, which was obviously 0. And then we had a couple of factors we defined. Obviously, G is 9.8. And then the Ks we calculated using the equation shown to the right, along with the LO and L hat. We also had to find a couple other energies, and we used that via other equations shown in the introduction slide. To finish the tracker simulation, we also had to calculate the forces and update velocity and position formulas, which is Newton's second law, shown in the first slide as well. And energy changes were calculated using the delta E system equations used on the introduction slide. So here you can see that for the energy changes, we have inputted various factors of the overall equation in order to break it down and have it calculate the right numbers. The computational results yielded these 3 graphs. First is a change in energy versus time, which shows those individual energies that we broke down earlier and inputted into our code. And then the X position versus time and Y position versus time of the computational and the experimental model. And you can see that the X and Y graphs are very similar, and you can also see that the delta U spring and delta U gravity are complete opposites of each other. So they oscillate in different directions, not oscillate in different directions, but they cancel each other out, and we'll see why in a little bit. So for some follow-up questions, we first had comparing oscillation periods of X and Y positions from tracker. So we did this by looking at each period from, let's say, like a low to a low. So we can see it on this image to the left, and the gap between each oscillation hitting the x-axis, for example, is one oscillation period. So the average for all of the ones shown here was about 1.614 seconds, and the average oscillation period for Y was about 1.425 seconds. The difference between this was 0.189 seconds, and the reason that these two could be different are for a variety of reasons, such as drag forces that weren't accounted for either in the computational model or the experimental model, incorrect center of mass, so as we clicked and tracked, it wasn't lining up 100%, and then other various versions of tracker error. Another question we had was, is the energy principle satisfied? And the answer to that is yes. So we can see that via the slide that had a bunch of different colors on the one graph, and I had stated recently that both the delta U gravity and delta U spring are opposites of each other, meaning that they cancel each other out. And according to this delta E system equation, if they cancel each other out, then the energy principle is satisfied.